Hi, this is Dr. Sridhar back with you with another video. In this video session, I am going to discuss about basic terminology like what is the definition of nodes, branch and closed path, what is the necessity of defining all these three parameters, and what are the Kirchhoff laws. In what way these Kirchhoff laws are helpful for solving the complex electrical systems, and this session we are going to reduce a complex electrical network into a simplified manner with the help of Kirchhoff laws. Coming to what is node, branch and closed path. Node is nothing but it is a terminal of any branch of a network or an interconnection common to two or more branches of network is called a node. Node is nothing but it is a joint. Now whenever two conductors or two wires are connecting together, now definitely they will form a common point. That common point is nothing but it is a node. If more than two elements meet a node, then it is called principal node. Now next, branch. A direct path joining two nodes of a network or graph is called a branch. A branch may have one or more elements connected in series. Now suppose if there are two number of nodes are there, if we are joining the two nodes with the help of one connecting wire, then that wire represents a branch. That branch is joining that two adjacent nodes. Now there is a formula to find out how many number of branches are there in any closed loop. The number of branches are is equal to number of loops plus number of nodes minus 1. Of course, this formula it will be very helpful for us in the forthcoming videos. And last one is a closed path. What is the closed path? It is a path which starts at a node and travels through some portion of the connected network and again terminates at the same node where it has started. That is nothing but closed path. Closed path starting and terminating point is same, but it will be traveled through the some portion of the remaining electrical network and terminates back to the same point. That is nothing but it is a closed path. Suppose if that path is not terminated where it has originated, then it is not a closed path. That may be a open path. So like this, we are going to define what nodes and what are the branches and what are the closed loop paths. Now, I have given one simple example. Now, in this one, we can mark where the nodes have been marked. The nodes are clearly mentioned with some green arrowheads, and branch is also represented with red arrowheads, and in violet color I have represented loops also. I hope this basic terminology is very clear to you all. And coming to the Kirchhoff laws, in this example there are three number of loops are there. The three number of loops and that branches have various resistances with a different value of it, and there is one voltage source is there. So in this electrical network, there are three loops are there. There are three loops means, suppose if you want to represent that three loops into a simpler loop, then you have to eliminate loop by loop slowly. Then that is nothing but that is a process of reducing a complex electrical network into a simplified electrical network. This can be achieved. We can simplify any complex electrical networks with the help of some fundamental laws like Ohm's law, Kirchhoff laws, and other electrical reduction techniques are there. That other electrical reduction techniques we are going to discuss in the forthcoming videos. But in today's video, video session, we are going to talk about what are the Kirchhoff laws and how these Kirchhoff laws will be helpful for us to reduce a complex electrical network into a simplified electrical network for analysis purpose. Suppose if we want to find out what is the current through R2 in the given network, or what is the current through R3, or what is the voltage drop across R4, what is the voltage drop across R3. Like this, if we want to determine the currents and voltages across or through any electrical networks or electrical branches, then these Kirchhoff laws will be highly useful for us. So coming to this Kirchhoff laws, in 1845, a German physicist Kirchhoff was described relationship of two electrical quantities, that is current and potential difference inside a circuit. So this Kirchhoff has been divided his theorems into two, that is the first law and second law. First law talks about the current and second law talks about the voltage in a completely closed path. Now, as per this Kirchhoff's first law, this is related with the current flowing inside a closed circuit, and it is called as a Kirchhoff's current law. In short, it can be represented as KCL. And second one is Kirchhoff's second law. It deals with the voltage sources of the circuit, which is known as Kirchhoff voltage law. This is KVL. Now, I have given a simple loop. In this one, again, for better understanding, I have marked very clearly what you mean by the loop and what you mean by the branches. And in this single loop electrical network, the current is delivered by the voltage source Vs, and it is passing through R1 and it is passing through R2, and it is again terminating at same electrical voltage source at negative terminal. Originates at positive terminal. The current is originating at positive terminal of the voltage source and terminating at negative terminal of that voltage source. The current is passing through R1 resistor and R2 resistor, and it is coming back to the supply source. A simple thing we can conclude here, that is the current is only one current is originated by one voltage source, and the current is passing through R1 and R2, and R1 output, the second terminal of R1, that is nothing but the negative terminal, it is connected to the positive terminal of R2. It means R1 and R2s are connected in series. So as long as the network is, the elements are connected in series, the currents or the current passing through the elements connected in series is remains same. This is very, very important. This will be helpful for us in determining the equivalent of series electrical circuits. And Kirchhoff's current law, that is KCL. The statement of this KCL is total current or charge entering a junction or node, that is a meeting point, is exactly equal to the charge leaving the node, as it has no other place to go except to leave, as no charge is lost within the node. Now, from this statement, it is very clear that node will not consume any electrical energy. So, if the node is not consuming any electrical energy, then what it means, whatever the current it receives, it will pass on through the remaining electrical network without loss of any electrical energy at that particular meeting point or junction. So, in the simpler terms also, this KCL can be defined as the algebraic sum of all the currents entering and leaving a node must be equivalent to 0. So, how much of current, how many branches are terminating at that particular node, and how many branches are originating at that particular node. Now, originating and terminating branches will carry some amount of current. So, incoming current with respect to that particular node and outgoing currents with respect to that particular node, where you have working to get the total analysis, where exactly you are concentrated your analysis to determine the currents and voltages, etc. Now, you have to take that particular node as a reference node. With respect to that reference node, how many branches are terminating at that? That is nothing but the incoming branches. How many branches are leaving that node? Those are nothing but the outgoing branches. So, total current in the incoming branches must and should be equal to the total current in the outgoing branches. So, that is nothing but algebraic sum of all the currents entering and leaving a node must be equal to 0. This idea by Kirchhoff is commonly known as the conservation of charge. So, there is no drop of any charge at that particular node. So, this statement is nothing but it refers to the conservation of charge. So, this is nothing but I exiting plus I entering. So, I exiting means the current which is leaving that node. I entering means whatever the current it is entering to that particular node, the algebraic sum is nothing but it is 0. So, we have given a simple geometry of a node with different branches, and here we have taken 5 number of branches. In this 5 number of branches, the current carried by the first branch is I1, current carried by the second branch is I2, current carrying by the third branch is I3, and current carrying by the fourth branch is I4. Similarly, current carrying by the fifth branch is I5. Now, if you could keenly observe the direction of orientation of that particular current, that is very, very important. Now, that will be very highly useful to determine whatever the KCLs. Now, in this one, I1, I2, I3. So, that is nothing but the currents in first branch, second branch and third branch. These 3 branches are carrying the current towards the node. And fourth branch and fifth branch are carrying the current, and the direction of that current is nothing but it is leaving the node. So, incoming currents are I1, I2, I3. Outgoing currents are I4 and I5. So, exiting current is nothing but the I4 and I5. Entering currents are I1, I2, I3. So, algebraic sum of all these currents are nothing but 0. So, entering current is I1 plus I2 plus I3 is equal to, so this can be written as I1 plus I2 plus I3 is equal to whatever the exiting currents I4 plus I5. Now, if we are simplifying this, I1 plus I2 plus I3 minus I4 minus I5 is nothing but the 0. Now, this is nothing but summation over at a particular node, summation of currents is nothing but the 0. So, this is nothing but the conservation of charge. So, this leaving currents here, it was clearly represented with red color. I4 plus I5 is nothing but the I1 plus I2 plus I3. So, these 3 currents are nothing but the incoming currents, and I4 plus I5 is nothing but the, this is the outgoing currents. So, this Kirchhoff current law, once again I am repeating, the algebraic sum of all the currents entering and leaving at a node must be equal to 0. Kirchhoff voltage law. Kirchhoff voltage law states that in any closed loop network, the total voltage around the loop is equal to the sum of all the voltage drops within the same loop, which is also equal to 0. See, in the previous current law, that is Kirchhoff current law, we have concentrated completely on the current analysis, or how if we want to analyze the currents. Now, KCL is useful. Now, Kirchhoff voltage law, in this loop, in this particular law, now we are working on loops category. In the KCL, we have concentrated on the nodes. Everything we have referred with respect to a node. Now, at every node, you can apply the KCL. But KVL, coming to the KVL, now you have to concentrate on the loops. Now, how many loops are there? In that any loop, if you want to apply the KVL, then you have to calculate potential difference, or that is a voltage drop, or the voltage appearing across the elements in that particular closed loop. Then algebraic sum of all the voltages in the particular loop must and should be equal to 0. That is the Kirchhoff voltage law. The algebraic sum of all the voltages within the loop must be equal to 0. This idea of Kirchhoff is known as the conservation of energy. KCL is conservation of charge, and this is nothing but the conservation of energy. So, here we have taken a simple one loop electrical network. Between A to D, one voltage source is connected. Between A to B, so here A, B, C, D, all these are nothing but the nodes, basic nodes. Now, between A node and B node, one resistor is connected. The voltage drop across that resistor is VAB, and the resistance value is R1. Between node B and C, R2 resistor is connected. Then it is assumed that the voltage drop across R2 is VBC. Between C and D, the voltage drop is VCD, and the resistance was assumed as R3. Between D and A, there is one voltage source having a voltage value of VDA. Here, there are 3 resistors and one voltage source is there. These 4 elements, if we are joined in a proper portion like this, as it was shown in the figure, then we can develop or we can see one simple closed loop. Now, once a loop is available for us, if loop is there, then you can directly apply the KVL to know the voltages or whatever the resultant voltage in that particular loop. Now, as per the statement, it is very clear that the sum of voltages you can see in a closed loop must and should be equal to 0. Now, from our previous lectures, now in the last video, I have clearly given 4 thumb points. One is to identify the voltage drop across a resistor and its polarity with respect to the current directions, and whenever you are traveling through a voltage source and whatever the voltage it will have and what its polarity, whether it is positive polarity voltage or negative polarity voltage. Please kindly refer my previous videos, then it will be very helpful for us to identify the polarity of that particular voltage drop across every element in the closed loop, because without knowing the voltage drop or without knowing the exact sign of the voltage drop across any element in a loop, now this Kirchhoff laws won't be solved. So for simplifying this Kirchhoff voltage law, please kindly refer my previous videos. Now here in this one voltage source is there. This is positive plate and this is negative plate. Now with respect to this voltage source, what is our movement of direction? Now we are traveling like this. Now whenever you are traveling in a closed loop, now between D to A, our movement is nothing but we are first touching D, then we are touching A. So our movement of direction is like this. So whatever the voltage here, VDA is the voltage. Now we are traveling from negative plate to the positive plate. So definitely we are going to have some boost in the voltage source. So that sign is nothing but the positive. So this is plus VDA. Then across resistor R1, and the current direction is, it was assumed like this. And what about our movement? We are traveling in the same direction. So first we are touching point A, then we are touching point B. So we are traveling from point A to point B, and the current is also in the same direction as in the direction in which we are traveling. To find out the voltage drops or potential differences across the various elements. Now whenever the direction and the current direction and our movement are in the same direction, straight away you can mark it as a negative, and the drop is nothing but negative voltage drop. So whatever the voltage drop now, this is voltage drop is nothing but it was marked as minus VAB, or this is, suppose it current is I, then this is nothing but the minus I into R1. Then similarly that holds good for second resistance also. So this terminal is B and this terminal is C. Now the current is like this and we are traveling in the same direction. So as long as the direction and the current are in the same direction, so this is negative and the potential is nothing but the minus VBC. And third one is, one more resistor is there and this is C and this is D and the movement is like this. Now this is the direction of this. So what is this? This is the movement and current is also in the same direction. So as long as both are in same, then straight away the potential is minus, this is nothing but the VCD. So like this, we have calculated the voltages or the drops across resistors and the source voltage along with its polarities. Without knowing the polarities, we cannot develop a complete mathematical equation which refers to this completely closed path. So the algebraic sum of all the voltages within the loop must be equal to 0. So algebraic sum means first we are going to see this is supply voltage, that is VDA, this is plus, and then next one is across R1, so this is plus minus VAB, then plus minus VBC, then plus minus VCD is equal to 0. So if you are simplifying this, now VDA is equals VAB plus VBC plus VCD. So this is the mathematical equation which refers to KVL of a given electrical network. So this is the statement what we have given, VAB plus VBC plus VCD minus VDA is equal to 0. If you are simplifying that, now if you are bringing everything into left side, so VDA becomes minus VDA. So simple example, already we have discussed KCL and KVL. With the help of these simple examples, let us determine how effectively this KCL and KVLs are useful to identify a current in a branch or the drop across any element if the voltage is not known to us. Suppose in the first circuit, if you are seeing the 10 amps is the input current. So straight away, the 10 amps is nothing but this is the input current. Now at point A, this 10 amps current finds two parallel paths. One path is like this and then next path is like this, what it was marked here. Now from A to up to this point, there is no element here, and even if the element is there, then the resistance is nothing but the 0. As long as the resistance of any branch is 0, the drop is 0. So there is no drop at all from A to here. But whenever you are traveling from this particular point to point C, now from this particular point to point C, now there is a resistor is there. Now here we are not interested because I want to highlight here what is the importance of KCL. In this KCL, only currents are important for us. So it was assumed that through this resistor, the current is nothing but the I4. And through this resistor, the current is 5 amps. So clearly you see whether it is ohms or amps. Ohms are nothing but the units of resistance. A is nothing but this is the unit of amperes, that is the unit of current. So 5 amps is nothing but the current, that is the current passing through this element, and this I4 is nothing but the current flowing through this particular element. So here at this particular A, now if you could see at this particular A, the incoming current is nothing but the 10 amps, and this is divided into two branches. One current is nothing but the I4, then next current is nothing but the 5 amps. So as per the KCL, incoming current is nothing but the outgoing currents. So outgoing current is I4 plus 5. So whatever the I4 now, I4 is nothing but the 5 amps. That is clearly given here. So like this, KCL is used and KCL is applied at different nodes where exactly you want to identify some of the unknown currents with the help of known currents coming to that particular node or terminating or junctioning at that particular node. Similarly, at junction B, if you could see, with respect to this B, one is incoming branch. So this current is incoming, two are the outgoings. So with respect to point B, one incoming current is 5 amps. This is point B, and here this is point A. So one is 2 amps current, and then next one is nothing but this is a I3 current. So what about the I3 current? Just simply by seeing this, we can identify what it will be the value. So this is nothing but the 2 plus 3 is equal to 5 amps. So this is nothing but the 3 amps of current. Similarly, you can also calculate whatever the I5 current. Now with respect to C, now this is nothing but the node C. How many incoming and outgoing branches? So there are two incoming branches is there. This is one and this is the another. So one current is I3, this is also incoming, and one current is I4, and only one outgoing current, that is I5. So already you have calculated whatever the I4 and whatever the I3. So incoming current I3 plus I4 is nothing but I5. So I3 is 3 amps plus I4 is 5 amps. So I5 is nothing but the 8 amps of current. So this is anyhow here if you are marking one more node, anyhow this is also a common point. Now after C, let it be D. Now at this D, if you are marking the currents, incoming branches and outgoing branches. So incoming is 2 amps, and anyhow I5 is nothing but it is coming with 8 amps. Now totally how much of current it is leaving? 10 amps. Anyhow this is the 10 amps of current. So like this, KCL is very helpful for us to determine the currents, and with the help of known currents, we can easily identify the unknown current values at meeting at a particular node. So hopefully this example understand very clearly what exactly KCL and how effectively it will be useful to know the unknown currents at a particular node. Now coming then next one is Here, with the help of this electrical circuit, I want to find out what is the use of KVL to determine the voltages in a particular loop. So KCL is nothing but it only concentrate on the node concepts, and this is nothing but loops. So straight away I am marking here. Now I am traveling like this. So here through this voltage source I am moving from negative to positive. So this polarity is nothing but it is a positive terminal. Then this is a positive terminal, this is a negative terminal. I am traveling like this. Current is also, it was assumed like this. So this is the polarity is minus. Then this is a positive and this is a negative. So value here they have not given, and the current is like this and our movement is like this. So totally this is also a negative. And then from this is a positive, this is a negative, and current is flowing like this, and we are also traveling in the same direction. So this is also negative. See why we have taken plus minus plus minus plus minus, because this is a one resistor, this is a second resistor, this is a third resistor. It means the VR1 is the drop across one R1 resistor, and VR2 is the drop across R2 resistor, VR3 is the drop across R3 resistor. All these three resistors are connected in series. As why? Because the current, whenever it is leaving this battery source, from there onwards, now up to the terminating instant, the current value is, it will not change, because all these three resistors are connected in series. Now, if there is a change in the current value, it may not be a series connection, it is something else. Based on the current magnitude and in what configuration the elements are connected, that tells us how many in the complex electrical network, how many of them are connected in series and how many of them are connected in parallel, and whatever the resultant connection, that we will see in the forthcoming videos. Now, like this, we have marked different potentials. Then algebraic sum. Algebraic sum is nothing but the VR1 plus VR2 plus VR3, because all these three are negative and this is only positive. So if you are bringing everything into one side, then minus VR1 minus VR2 minus VR3 plus 10V is equal to 0. 10V is nothing but the value of this is nothing but the 10 volts. That's, and VR1 they have given 4 volts and VR2 is unknown to us and VR3 is 2 volts. So 4 plus 2 minus 10. Then VR2 we are going to get as a 4 volts. So like this, we can use Kirchhoffs laws. Either it may be a KCL or KVL. Now we can easily identify various electrical quantities based on our requirements in the complex electrical network. I hope this video gives basic idea about Kirchhoffs laws and with some suitable examples. Thank you very much for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.